Have you ever wondered how Perplexity seems to know exactly what you need faster than you could ever search for it? You're asking a question just like you do on Google, but instead of links to websites, you get a perfectly crafted answer, all distilled from multiple sources across the internet. What you're seeing here is Retrieval Augmented Generation, or RAG, that is built on top of the large language model. RAG is like a knowledge distillation layer sitting on top of the internet designed to deliver answers. But how does it work? What makes it so powerful? That's what we're diving in today. In this video, you and I will go on a journey to understand RAG. We'll break it all down from the fundamental building blocks to the big picture. So by the end, you will have an intuitive understanding of how RAG powers tools like Perplexity and transforms the way we access knowledge. Let's dive in. Let's quickly recap what a large language model or LLM is. These are massive models pre-trained to do one simple yet powerful task: predict the missing words in a sentence. They have been trained on nearly the entirety of the internet and carefully curated high quality datasets. Through this repetitive brute force process, LLMs develop a deep understanding of the language. Well, not too deep, that's the topic for another day. But along the way, unexpected emergent abilities start to show up. But here's the catch: this training only made LLMs good at filling in blanks, not answering complex user queries. Enter reinforcement learning with human feedback, a new training mechanism that fine tuned LLMs to engage more effectively with us. Yet, with these improvements, there's still a challenge. LLMs struggle to answer questions based on recent events or new information stored outside their so called parametric memory. And that's where RAG, or Retrieval Augmented Generation, steps in, bridging the gap and enabling LLMs to stay relevant and respond to fresh, real world events. Let's start with the basics: the query. At its core, a query is just a question or anything you're looking for an answer to. It can be something as straightforward as what is RAG, or even requests like what should I get my nephew for his birthday. It could be also something that needs up to date information like what's the weather today, or it might be a deep philosophical question like why do we exist. A query is simply the thing you're trying to find out, no matter how simple or complex. But here's the thing: to make this query searchable in our vector database, which we will talk about in some time, we need to convert it into a different format. So that's where the embedding model comes in. So let's start by building a simple embedding model together and then gradually make it more complex. The goal of the embedding model is simple though: to convert your human readable query into an LLM friendly format that is more meaningful. Let's take the first query: what is RAG? Now take a moment, pause if you'd like, and think about how you might transform this query into a format that's easier for an LLM to understand. So, taking the query, what is RAG, we break it into individual words. This process is called tokenization, specifically a word tokenizer. Now, the next step is to build a vocabulary. Just like we humans know a certain set of words, we can teach LLMs to recognize only a specific set of words. For simplicity, let's make our LLM knows just three words: what, is, and RAG. We'll assign each word a unique number: what gets 1, is gets 2, and RAG gets 3. And to keep things simple, we'll ignore the question mark for now. While using numbers is a straightforward solution, we can do even better by representing words in a more advanced format called vectors. One way to do is with a one hot vector, where each word is represented by a vector with 1 in a specific position, first, second, or third in this case, depending on the word. When we turn words into vectors, something cool happens. We get a nice geometric view of our query. What is RAG? Since we are working in 3D, we can think of our words as points in space. So, here's how it works. What shows up as a vector on the x-axis, is shows up as a vector on the y-axis, and RAG is represented as a vector on the z-axis. Now, I want you to pause for a second and think about it. how would we represent the whole question, what is rag, in this vector space? The easiest way is to take the sum of these vectors. By doing that, we are combining what is and rag into one single vector that captures the full question in this 3D space. And look at what we have just done. We have transformed a bunch of words into something that these large language models can process and understand. Pretty cool, right? And also, if I might add, we have created our very simple embedding model. Okay, so here's the deal. Our embedding model is pretty simple right now, and we need to find ways to make it better. But here's the first issue. So far, our tokenizer and the embedding model can only understand 3 words. And obviously, we wanted to understand more than that. Now, if we stick with something like one hot encoding, we hit a problem pretty quickly. As we add more words, the size of our vector, or what we call the dimension, grows. And this is where things get tricky. The more words we add, the more memory it takes up, and the more computation power is needed. And honestly, we don't want to deal with either of those problems. Take a look at Llama 3 from Meta, for example. Its tokenizer uses 128,000 tokens. So, using our approach, we would need a vector of 128,000 dimensions. That is expensive and inefficient. So here's another big problem with one-hot encoding. It doesn't let us do any kind of semantic manipulation in the vector space, and that's a big deal. Let me show you why. Imagine you have the word king as a vector. Now, what if we subtract the vector for man and then add the vector for woman? In a good embedding system, this kind of math should give us something close to queen. Why does this matter, you ask? Because these kinds of manipulations show that the vectors, or more simply the numbers, carry semantic meaning. Without that, we are missing a huge part of what makes embedding models so powerful. This is where a groundbreaking paper introduced a game-changing solution called Word2Vec. It tackled both problems, reducing vector size and making vectors rich in semantic meaning. Word2Vec works by using the context of words to learn their relationships. It does this in 2 ways. It's called CBOW, or continuous bag of words, predicts a word based on its surrounding words, and skipgram predicts surrounding words based on a given word. Both of these are outside the scope of these videos, but essentially, once trained, the model generates smaller vectors that encode rich semantic relationship. This allows us to do things like king minus man plus woman equal to queen, because the vectors capture the deeper meaning like gender and hierarchy. Alright, let's do a quick recap together. We started with one hot encoding and used simple addition to represent our query. It was a basic approach, but it worked as a starting point. Now, instead of that, we can use Word2Vec to convert our words into a richer, more meaningful representation or vector, but then instead of just summing those vectors, we bring in a dedicated embedding model, something more advanced, like a transformer model. With this setup, we can generate a far better vector for our query, what is rag. So far so good, right? So let's build our very own retrieval system together, step by step. First up, we need to take all our external knowledge, just like our query, what is rag, and convert it into vectors. For example, imagine we have some text from Wikipedia. In first glance, it's long, right? And here's the problem. Large language models have a fixed context window, which means they can't process the entire text all at once. So what do? We break it into smaller chunks, a process fittingly called chunking. In this case, I have divided the text into chunks of 100 characters, but there are plenty of other ways to do it depending on the task. Once we have these chunks, we treat each one like a query, converting them into vectors just like we did earlier. And here it is. And just like that, we have divided this entire large text into a bunch of vectors which we can play around with. Let's go back to our 3D space and plot the vector for what is rag again. To keep things simple, let's represent all these vectors as points in the space now. Now, all the chunks we created earlier are also plotted in the 3D space, each occupying its own unique position. This is what we call a vector database, a fancy name for a space where your queries and external knowledge live as points. Retrieving information here is like playing a game of finding the closest points. In our 3D example, this means calculating the Euclidean distance between the query point and all other chunk points. The closer a chunk point is to the query, the more semantically similar it is. By picking the nearest points, we're essentially retrieving context that an LLM can use to answer the query. And here's the cool part, we can fine tune what gets considered relevant. By setting a distance threshold, we exclude any chunk points that are too far away, ensuring the retrieved context stays meaningful and focused. Now that we have sorted the retrieval part, let's dive into the A in RAG augment. Picture those red points in our 3D space clustered near our query point, which is in white. These points represent specific text chunks, each one a 100 character slice of our original long document. For simplicity, let's say we retrieve the 4 chunks as shown here. The augment step now is about taking this retrieved text and using it as additional context. We pass these chunks to our prompt, which then becomes the input for the LLM, and that's it. Augmenting is simply enhancing the input with relevant context to help the LLM give more accurate and meaningful answers. Pretty straightforward, right? With our enhanced prompt packed with all the relevant context, we hand it over to an off the shelf LLM like Llama, and voila, you get the response that's tailored specifically to your question. And that, my friend, is essentially what RAG is, a clever system that acts like an on the fly cheat sheet for the LLM, helping it craft accurate and insightful answers just for you. It all sounds great so far, and you're probably itching to implement RAG yourself. But before you dive in, let's talk about some challenges you might face. RAG operates on a key assumption. Your query vector will closely align with the context vectors in the same space. But what happens when that's not the case? Imagine all your context vectors are tightly clustered around your query point, or worse, they are scattered far away from it. Should you still retrieve those points? So these situations can arise for several reasons. Chunk sizes may not be optimal, your embedding model might not be performing as expected, your query might be complex or too simple. There are too many technical quirks that might creep in. That is why it's absolutely critical to ensure that every subcomponent in your rack pipeline is functioning properly for the whole system to work seamlessly. When it comes to handling complex queries, there's a really elegant solution and it's best explained visually, which is why I'm showing it here. If your query feels like it's trying to do too much, you can break it down into smaller, more manageable subqueries using an LLM. Each subquery is treated individually to retrieve relevant context. Think of it like this, instead of relying on a single shot to hit a bullseye, you can now have multiple shots, increasing the likelihood of finding the right context. And here's where it gets even better. If the same context is retrieved for multiple queries, you can rank it higher, making it even more credible. This approach is part of an advanced RAG strategy, and honestly, it deserves its own dedicated video. With all that said, RAG is an incredibly powerful tool. Think about it. Before RAG, when you search for something on the internet, you'd get a list of websites ranked by keywords, but you still had to sift through them all to find the answer you were looking for. It was like being given a treasure map but still needing to dig through the dirt to find the chest. Now, with RAG and LLMs, there's a knowledge distillation layer that I like to call between you and the internet. Every time you ask a question, a web search happens in the background. But instead of you manually sifting through the dozens of pages, the LLM acts like a wise guide, summarizing all the information and giving you the answer directly. In conclusion, RAG transforms how we access information, grounding LLMs in reliable, up to date sources for accurate and tailored responses. It's scalable, cost effective, and enhances trust with source attribution, all while bridging the gap between fast data and meaningful insights. RAG isn't just a tool, it's a leap forward, making knowledge truly serve humanity. So, you and I have been on quite a journey together. We built RAG step by step, explored its challenges, and celebrated where it truly shines. If you have made it this far, it tells me you enjoyed this video as much as I enjoyed creating it for you. If that's the case, it would mean the world to me if you hit the like button and subscribed to my channel. Not just for me, but so others can discover this content the same way you did. Thanks for being here. It's been amazing sharing this with you. See you in the next.